Need to engage or utilize the chain rule for the first one? Yes, no?
Sorry, I'm thinking no.
Right, and no is the correct answer. We can go straight and differentiate each individual term. So we have separate functions, no two functions in one. So I'm just going to go through it just for some practice. So the derivative here, dy dx, would be, when you differentiate 5x squared, what will we get?
10x.
Yeah, 10x. You differentiate 3x, we get 3. Differentiate sine x, we get cos x. So there was no need for a u substitution. Good. What about this second one?
Yes, sir.
Great. So what is your u? What's your inner function then?
X squared minus 6, sir.
Wonderful. Great. And we rewrite y as y is equal to u to the 5th power, which is x squared minus 6 to the 5th power, right? And then you apply your dy, du, dx. Good. What about the third one? Do we need a u substitution?
Sorry, I'm thinking yes.
Yes. And that is correct. This is an exponential function. And what will u be equal to?
E, sir.
Go there for it. Someone else?
Five x, sir.
Very good. So u is equal to 5x. So we rewrite this as y is equal to e u. Right? E to the u power. So that's an exponential. But what about the fourth one?
So I'm thinking that's a product rule.
Product? Sure.
Not sure, sir.
Alright, so you have to get cos of something, right? So it can't just be cos times something. It has to be cos of something. So in this case, it's cos of 5x plus 2. So it's one function. And this one function is a composite function. So in this case, u would be equal to 5x plus 2. So, and y would be equal to cos u. So let me explain, Mr. Sugri. If we had something like, instead of cos 5x plus 2, we had, I'll show you how it could be a product rule. If we probably had cos x times 5x plus 2. So you see, there's already something with the cos x. Right? In this case, it would be a product rule because cos x is one function and 5x plus 2 is another function. But if, like how we had it there, cos, we find the cos of this.
Oh, so sorry, the cos is attached to the using the distributive law.
Well, no, this is not distributive law. Remember, you have to find cosine of something. You can't just write cos by itself.
Okay, sir.
Right? So that's why I write cos. It has to be cos of something. So what about the final one? Y is equal to 5x squared minus 3 over cos.
Sorry, I'm thinking quotient.
Yeah, so do we have to employ the chain rule here?
I'm thinking no, sir.
Anyone else? Yes, no? Do we have to employ the chain rule? Or I need to hear from someone else?
No, sir.
No. So what about if it was cos 6x at the bottom? Would we have to employ the chain rule at some point?
Yes, sir, because cos is equal to something.
Very good. We are costing another function. If it's x by itself, it's okay. If it's u by itself, it's okay. But once the function is independent, then you need, once another function, you need to utilize the chain rule. Right? If it's x by itself, that's fine. All right, so I hope you have done a good evaluation of yourself where you stand in terms of applying the chain rule. I would advise that you look at a YouTube video on the chain rule. So with that, we can look at the rate of change. We'll just do this one example. Now, all of this that I did here, right? This is something as mathematics teachers, I know I don't get to talk to you often about your classroom practice. But as mathematics teachers, you have to be very, very careful of how you teach. That is why prerequisite is very important. If you go to a class to teach algebraic fractions, what's the first thing you need to ensure? One of the first things.
So watch a YouTube video.
You sure? You are going to teach this class. And your topic today is algebraic fractions. What do you have to consider as the teacher going to these students? There's no foundation, right? So I am using this as a reference to why I didn't move on with related changes. We did chain rule. But then you can't take things for granted. You might say, but I did this with my students. It's important to check for previous knowledge. And that's one of the main reasons people don't learn mathematics. I'm not blaming teachers, but I'm saying people don't learn mathematics because certain fundamental prerequisites are not there. So we are actually building on nothing. The students came from the primary school with little or no foundation, but we have to carry a syllabus. So that's why it's important. And the next thing I want to say, usually I don't teach calculus if I didn't teach the algebra course. It's a sore point. I found myself in situations before. I don't teach calculus to students unless I taught them algebra. Because algebra, as I said before, is the prerequisite of calculus. And you need to have a strong understanding of algebra to be able to really master calculus. Right?
Yes, sir.
So going back to the question, it says, let me find it. I'm not going to put you on the spot page. Yeah. So it says, yeah. If the radius of a sphere is increasing at 2 cm per second, find the rate at which the volume of the sphere is increasing when the radius is 3 cm. What we have here, we have a sphere, maybe it's a balloon in a spherical fashion. Forgive me, I didn't do art. Right? Yeah, so let's say we have a balloon in a spherical fashion. Let me just, this is better. This is the radius. Now, normally if you get a question on rates of change, they normally give you the formula. So if you were dealing with a sphere, then you'll get a volume formula. Can anyone recall the formula for the volume of sphere out of their head?
So I'll make a try. 4 pi r squared.
Reasonable. I'll go there for it. So it's 4 thirds pi r cubed. Remember volume, right? Has to be in cubic units. Right? So that's a go there for it. So the volume of a sphere, this is the formula, 4 thirds pi r cubed. When we read this question, we are given one change, and the change is the radius against time. Because they said the radius is increasing at a rate of 2 cm per second. So what is it saying? Every second it's growing by 2 centimeters. So as this balloon is being blown, after 1 second, this radius increases by 2 cm. So probably after a second, this is what it will look like. I know I'm drawing a circle. Another second, it will increase by another 2 cm. So this is what they're talking about. As you keep blowing air into the balloon, the spherical figure, the radius is increasing every second by 2 centimeters. So that's basically what it's meant. Now to represent this rate of change, let me take a step back. We represent the rate of change of y with respect to x by writing what? dy dx. Right? So if we want to represent the rate of change of radius with respect to time, how can we write that? A change in radius with respect to time.
So dy dt.
Good effort. Very good effort. But radius represents r, right? So it will be dr dt. So this simply means it's the change of the radius with respect to time as time changes. 1 second, 2 seconds, 3 seconds. So we're not going to represent time in terms of s. We use the letter t to represent time. So the rdt is the rate of change of the radius with respect to time. So what we're given here, this rate is our rate of change of radius with respect to time. So our dr dt, they give us that. That's 2 cm per second. Right? Now, I'm going to try my best to break this down, but I will definitely need to use a few examples. So let me see if I can read one here before we move on. Great. 320. So just listen to this and tell me which rate of change we are given. Let me see if you can pick this one up. Air is being pumped into a balloon, a spherical balloon, at the rate of 54 centimeter cube per second, sorry. So let me read that again. Air is being pumped into a spherical balloon at a rate of 54 centimeters cube per second. Again, air is being pumped into a spherical balloon at a rate of 54 centimeters cube per second. Now, what will that centimeter cube per second represent? Is it volume? Is it radius? is it area? I want you to think about it. They're saying air is being pumped into a balloon at a rate of 54 centimeters cubed per second.
Sir, volume?
Why do you say volume?
Because it's cube, sir.
Wonderful. So that 54 cm cube per second is actually our change in volume with respect to time. I'm just showing you how we get our formula. So if it's cm cube, we know it's talking about volume. So my change in volume with respect to time would be 54 cm cube per second. Right? So that was a good effort. So let me give one more, but I want someone else to give it a try. Let's see. Good. If the radius of a circle increases at a rate of 2 cm per second, the radius of the circle increases at a rate of 2 cm per second. So what are we finding? What are we given there? That 2 cm per second, what is it telling us? Rate change. Anyone else? 2 cm per second. This is a giveaway. The radius of a circle increases at a rate of 2 cm per second. What over dt are we given here? Anyone?
Sir, can I go?
No, give some. Let's try to get someone else, please.
Sir, dr.
Wonderful is the radius. They're telling us that the radius is changing. Very good. So it would be dr over dt, the rate at which the radius changes in terms of time. Right? Dr dt. Great. So I just wanted to establish this. It wouldn't be perfect for now. To be honest, as a student, I took a long time to understand rates of change. I had my own way of finding it. Right? Good. So let's go back to the original question. So the radius is increasing at 2 cm per second, and they want us to find the rate at which the volume is increasing. So they want the rate, they give us the rate at which the radius is increasing. So they give us dr dt. And this is the method I came up with. What is given and what they want. Looking at the question, they want the rate at which the volume is increasing. So what they want from us, they want dV, the change in volume with respect to time. Is this clear with everyone?
Yes, sir.
Anyone else?
Yes, sir.
They give us the rate at which the radius is changing. So that's dr dt, and that's 2 centimeters per second. But they're asking us for the rate at which the volume is increasing. So they want from us dV dt. Now, what we need is a middle variable. What should we put in the middle? So this is how I do it. So I want dV dt. I already have dr dt. What do I need to multiply by? And when I cancel out, I'm left with dV dt. Because this is what I want. So this middle one we're trying to find out. Who should I put here?
Sir, dt over dv.
dt. But if I put, I'll put that, right? If I put dt over dv, look what will happen. I will
still won't leave with what you want.
Yeah. So I can't use that, but that's a good effort. At least you're thinking now. Good. So what should I put? So that when I cancel,
turn and put the same thing again.
Sure. Look carefully. I want to end up with dv dt. I already have the t dt, but I don't want the r.
Sorry, put dv over dr.
Wonderful. That's what I need. dv and dr. So if this and this cancel out, I'll be left with dv dt. And that's basically the mystery in this. So all I need is to find dv dr. That's what I need. That's the middle one. Once I get dv dr, I'll be able to get, when I cancel out, I'll be left with dv dt, which is what I want. Right? So we'll go this over one more time. Good. So according to the information we are given, dr dt, that's a change in radius over time. Are we good?
Yes, sir.
They ask us to find the change in volume, the rate at which the volume is changing. So that's a change in volume over time. In order to find this, what they want, so I'm going to say want, I know, or given, and I need to find something in the middle. Right? So because I want dv dt, I'm already given dr dt. I need this middle one here. And we agreed just now that if I want to be left with v and t, then I need to infuse a v here, and I need to bring a r to cancel out with this r. We don't have to cancel it out, but I'm just showing you. So what we need here to complete this puzzle is dv dr. Is this good with everyone? Remember, we are talking about volume, and the volume of a sphere is 4 over 3 pi r cubed. Now, if I differentiate this volume formula, I'll get dv with respect to r. So if I use r as my variable, I'll get dv dr. So using r as our variable, what's the power of r? I multiply by 3. So when I multiply 4/3 by 3, what will I get?
4, sir.
4. I put back pi because pi is a constant, so it's 4 pi. And what do I do with my power 3?
Differentiate, sir?
No, I'm differentiating already. So I multiply by the power 3. So what's the next thing to do after I multiply by the power?
Minus 1.
So it will be r squared. So this here is my dv dr. 4 pi r squared. So when I differentiate my volume formula, I get my volume with respect to r. So that's my dv dr that I want here now. So normally what they do, they would give you the formula that they want you to use. That's the only way I can get dv dr, because I knew what the volume formula was. So to get my dv dt now, all I need to do is some substitutions. dv dt is equal to, my dr dt is 2 centimeters per second times, what's my dv dr?
4 pi r square, sir.
4 pi r square. Can we simplify this? I'll take out the units here for now. So dr dt is 2 times 4 pi r squared. When we simplify this, what will we get?
8 pi r square.
Very good. 8 pi r squared. So this is our formula if we want to know the change of the volume with respect to time. But they ask us for a specific time. They want it when the radius is equal to look back at the question. When r is equal to
3 cm.
Very good. So what do you think we'll do with that 3?
Substitute it in the r.
Very good. So dv dt, the change in volume, will be equal to 8 pi 3 squared. And 3 squared is what?
9, sir.
9. So it will be 9872 pi. And what do we measure volume in?
Cube, sir.
So it will be cm cube. And it's a rate, so it has to be cm cube per second. That's what our unit will be. Cm cube per second. So I know this one will be a little tough one for you to bite. Would you like me to go it over one more time?
Yes, sir.
Anyone else?
Yes, sir.